All right, welcome. Today we're going to dive into two really cool puzzles from linear algebra. They pull back the curtain on some of the hidden and honestly kind of surprising rules that connect matrices and vector spaces. So let's get right into it.
So, one of the first things you've learned about matrices is that the order you multiply them in really matters. A times B is almost never the same as B times A. But that makes you wonder, right? Are they just completely different beasts? Or do they have some kind of secret connection, some shared DNA? Well, that's our first puzzle. We're about to investigate what I like to call the case of the traveling eigenvalue. The question is pretty simple. If a number is an eigenvalue for the matrix AB, is it automatically an eigenvalue for BA too? Let's find out. Okay, so to get this proof off the ground, we'll start with what we know. Let's just assume we have an eigenvector V for the matrix product AB. All this equation says is that when AB acts on V, it just stretches or shrinks V by some non-zero amount, lambda. And lambda is our eigenvalue. This is our jumping off point. And here comes the magic move. This is the little bit of creative thinking that makes the whole proof just click into place. We're going to invent a brand new vector, u, and we'll define it simply as our original eigenvector v multiplied by the matrix B. I know it might seem a little random, but trust me, this is the key. Now, it is absolutely crucial that this new vector u isn't the zero vector, and here's why it can't be. If u, which is bv, was 0, then abv would be a times 0, which is 0. But hold on, we started by saying abv equals lambda times v, and we know neither lambda nor v is 0, so u has to be a non-zero vector. Okay, with that settled, let's see what happens when we throw the matrix BA at. First things first, we just substitute in our definition for u. So BAU becomes BA times BV. Now, because matrix multiplication is associative, we can basically just do a little shuffle with the parentheses. Instead of grouping it as BA times BV, we can group it as B times ABV. And look at that. This brings us right back home. That bit inside the parentheses ABV should look really familiar. It's our original definition. We know exactly what it is. It's just lambda times V. So we can swap it right in. And this is the final beautiful step. Since lambda is just a number, a scalar, we can pull it out to the front. That leaves us with lambda times BV. But wait a minute, what's BV? That's our special vector u that we created. So what have we just shown? We've shown that BA times u is equal to lambda times u. And there it is. Our new vector u is officially an eigenvector of BA. And even better, it has the exact same eigenvalue, lambda. The eigenvalue has successfully traveled from AB over to BA. It's such a clean, elegant proof. But did you notice I kept saying non-zero eigenvalue? What happens if lambda is 0? This is where our nice, neat story hits a plot twist. Does this perfect symmetry still work when the eigenvalue is 0, or does the whole thing fall apart? You know, for every single non-zero eigenvalue, the rule is rock solid. AB and BA perfectly mirror each other. But for the 0 eigenvalue, well, that mirror can shatter. Just because AB has a 0 eigenvalue doesn't mean BA has to have one. And you don't have to take my word for it. Let's look at a cold, hard counterexample. We'll use two non-square matrices here. Matrix A is a 2 by 1 column vector, and matrix B is a 1 by 2 row vector. So what happens when we multiply them? Well, A times B gives us a 2 by 2 matrix. But B times A? That gives us a tiny 1 by 1 matrix, which is really just the number 1. They couldn't look more different, could they? And here's the real kicker. Our 2 by 2 matrix AB has a determinant of 0. That means it's not invertible. And a fundamental rule of linear algebra is that any non-invertible matrix must have an eigenvalue of 0. Now, what about BA? It's just the number 1. It is perfectly invertible, which means 0 cannot be one of its eigenvalues. And there it is, our proof. The rule breaks down for 0. Okay, puzzle number 1 is officially solved. Let's move on to our second puzzle, which is going to take us out of the world of eigenvalues and into the realm of vector subspaces. This one is all about a case of perfect symmetry. So let's set the scene. For any linear transformation T, you've got its image, which is basically all the possible outputs, and its kernel, which is all the inputs that get squashed down to 0. We're going to start with a special assumption, that our entire space is the direct sum of these two things. Think of it this way. It means that every single vector in our space can be built in one and only one way by adding a piece from the image and a piece from the kernel. No overlap, no other way to do it. So here's the puzzle. if we have this perfect, clean split of our space into the image and the kernel, does that amazing property also apply to their orthogonal complements? Remember, the orthogonal complement is just everything that's perpendicular, or at a right angle, to a subspace. So is the whole space also a direct sum of the orthogonal complement of the image and the orthogonal complement of the kernel? Let's walk through the proof together. I promise it has a really satisfying aha moment at the very end. Our strategy here is actually pretty simple. To prove that two subspaces form a direct sum, we just need to show that the only thing they have in common, their intersection, is the zero vector. So we're going to grab any old vector v that lives in that intersection and then prove it has no choice but to be zero. Now, because of that special assumption we started with, we know we can break our vector v down into two unique pieces, a component v1 that comes from the image of t and a component v2 that comes from the kernel of t. And here it is, the aha moment. Let's take the dot product of v with itself. First, we'll substitute v with its two parts, v1 plus v2. If we distribute that out, we get v dot v1 plus v dot v2. Now let's think about that first term. We picked v from the orthogonal complement of the image, which means v is perpendicular to every single vector in the image, including its own component v1. So their dot product has to be zero. The exact same logic applies to the second term. V is also perpendicular to everything in the kernel, including v2, so that dot product is also zero. And what are we left with? 0 plus 0, which is just 0. It's a fundamental property of vectors that the only one whose dot product with itself is 0 is the zero vector itself. So we've just proven that our random vector v must be the zero vector. That means the intersection is trivial, which means the direct sum is proven. The symmetry is real. So, after all that, navigating through eigenvalues, counterexamples, and orthogonal subspaces, what are the big takeaways from solving these two puzzles? Well, first, we saw that even though AB and BA are usually different matrices, they have this deep link through their non-zero eigenvalues, which can literally travel between them. But we also saw that 0 is a special case, and sometimes it gets left behind. And second, we uncovered this really beautiful symmetry. When a space can be perfectly split into a transformation's image and kernel, that same perfect split is mirrored in their orthogonal complements. You know, these puzzles are a great reminder that even in a subject as well explored as linear algebra, there are still these elegant rules with surprising exceptions and these beautiful symmetries just hiding under the surface. It really makes you wonder, doesn't it? What other hidden patterns are out there just waiting to be discovered? Thanks for watching.